So we're going to finish off chapter 4 today with starting out with some more definitions, general education kind of stuff. We'll talk about rank, and nullity. And the guys I mentioned before, the fundamental matrix spaces, as like the row space, the column space, the null space, and the null space of the transpose of a matrix. So mostly definitions, and we're going to talk about how these guys allow us to say some more about the equivalence theorem. Rank we've actually seen before. So anyone remember what we said the rank was?
The number of pivots?
Right. The rank was the number of pivots. How can you actually now rephrase that in terms of what we did last time in 4.7? We were talking about the column space, the null space, the row space, all that stuff.
The dimension of the column space?
It's actually the dimensions of the column space of A. Which, by the way, it's actually going to be exactly the same as the dimensions of the row space of A, right? Because the row space, remember, this was the space that the basis vectors were the non-zero rows when A was put in reduced row echelon form. That's actually the same as the number of rows that have pivots. That's exactly the same as the number of rows that have pivots. The column space is when we picked out the columns corresponding to the number of columns that have pivots. So counting the number of columns gave you the rank. It is therefore by definition, well, the same as the dimensions of a column space or the row space. So you can connect our definition of rank to what we saw last time by dimensions. And how did we measure the dimension of something? What is the dimension?
The number
The cardinality of its basis.
The cardinality of the basis gives us the dimension. Okay? At least for vector spaces, there are things like with non-integer dimensions, but those are different kinds of objects. So that is your rank. The nullity of A, which you write out the entire word, the nullity of A. So this is another definition. This is the dimensions of the null space. So you can think of this as something like the number, if you wanted to put it down to a number that relates to a matrix, this would be the number of parameters for AX equals the 0 vector. All right, so if you try to solve that equation, the number of parameters in that equation is actually the dimensions of the null space. That will be how many vectors there are in your null, in the basis for your null space. What else do we want to define? Oh, there's an important theorem that comes from this. It's called the dimension theorem for matrices. So it says let squared necessarily. Let A m by n be a matrix, then the rank of A plus the nullity of A is what?
N,
Number of columns.
number of columns.
Okay, so which is?
Yeah.
Is the number of columns. And again, if you look at it in terms of the column space, right? This guy's telling you the number of columns that have pivots. This guy's telling you the number of columns that don't have pivots. But those are the only two kinds of columns there are. So if you take the number of columns with pivots and the number of columns without pivots, that's all the columns. And so the rank plus the nullity will always equal to the number of columns. And that is called the dimension theorem for matrices.
Actually, look, is the nullity of A, let's say there was one unique solution for A, like the AX equals 0.
And only has one solution, then nullity would be 0. Because
Okay.
there would be no columns that are parameters.
Okay, I see.
So
Oh,
this would be all of it. That would be
Yeah,
that would be
makes
0.
total sense. Okay.
Another note here before I continue. Of course, the rank of A is the same as the rank of its transpose. The same can be set up the nullity, but that can be set up the rank. Now, with this, we can extend our equivalence theorem. So at the end of this section here, they extended the equivalence theorem. They extended again at the end of 4.10, but I'd have to actually talk about some things in 4.10 before I can tell you that. So let's talk about the new equivalence theorem. So let A be a matrix. Then the following are equivalent. The following are equivalent means they're all true or all false at the same time. So if you know one of these facts, you know all of them. And if you know any one of these facts are false, you know that all of these facts are false. This letter A. And we start with A is invertible. B. Another thing you can tell me about this theorem.
You're already at this identity?
Reduced row echelon form of A is the identity. Something else you can tell me?
The determinant is not 0?
The determinant will not be 0. Something else you can tell me?
An equation of the form AX equals B has a unique solution.
Right. It is consistent.
Oh,
For every n by 1 matrix. In fact, it will have a unique solution. In fact, AX equals B. They put that as a separate item for some reason. Has a unique solution. Given by x equals A inverse times B. C, D, E, F. AX equals 0 has only the trivial solution. G, What else do we know?
A is the product of elementary matrices.
A is the product of elementary matrices. Is that all we knew so far, up to G? We have that, we have that, we have that, we have that, have that, have that, we have that. Okay, let's talk about some other, yeah, so that's all we knew so far, but in light of the last two sections we just covered, now let's add some more. What can you tell me about the rank of A?
It equals n.
It must be n. I. Can you tell me about the nullity of A?
0.
It must be 0. So any invertible matrix will have rank n and nullity 0. The dimensions of its row space will be n. Dimensions of its null space will be 0. And that can tell you something else. Therefore, rows of A are a basis for, let's say this is a matrix over a field F. Okay, so F can represent the real numbers, complex numbers, probably something else. We can take its rows to be a basis for what? Right, Fn. Okay. What about the columns of A?
Same thing.
Same thing. So the columns and rows will be a basis for Fn. So any invertible matrix, if I just take all its rows, that forms a basis for its domain space. And if I take all its columns, well, if I take all its columns, that's a basis for the domain space. If I take all its rows, that's a basis for the range space. J, K. I think that's all we have so far. There are a couple other things that are mentioned here, like the orthogonal complement. But I can tell you what that says, but I'm never going to mention that ever again. So, at places where linear algebra is a 2-semester course, that's kind of where the second semester would start, where you're talking about orthogonal complements and orthogonality and all that sort of stuff. But you can talk about the set of all vectors in Fn that are orthogonal to every row of A. We call that the orthogonal complement of A, and then we can start to talk about that. That can be a lot of stuff, but we'll stop there for now. So we'll know up to K. We know all this about any matrix. Once we know any one of these facts, we know all of these facts. So if you tell me, okay, these three matrices, these three vectors are a basis for R3, I know if I make them into rows and create a matrix, it's going to be invertible. It would reduce the identity. If it's a coefficient matrix for a homogeneous system, we'll only have the trivial solution. I'll know everything, right? And any one of these things you tell me, I will know all the others. And if I know any one is false, then I know all the others are false. That's pretty cool. We'll actually add a little bit more to this after we go over 4.10. But when you start to study really serious linear algebra, I mean the title of this course is Elementary Linear Algebra, so we're not expected to go very deep into it. But when you start to go into really serious linear algebra, having these facts in your head is going to be very useful because it helps you with certain intuitions. You would kind of know when something will or will not be true based on how the matrices involved behave. And so it's a very useful thing to know the equivalence theorem. It's a very big deal. But we will move on to 4.10. Properties of matrix transformations. Okay. And chapter 8 is going to go over this and kind of rehash it, generalize some things, and maybe fill in a few gaps, and we'll do that after, but let's actually just go through 4.10. I mean, in the ideal scenario, if I had the time to actually squash these two, I'd actually combine these two sections. Let's just do chapter 8 and chapter 4 in one. I think it would have been fine. But that's not how the textbook does it, so, and we're going by those sections, so we're going to do this. And again, I already mentioned this, so it's kind of jumping ahead, but at this point, I think we're all familiar with the idea. Matrices can represent linear transformations. Right? So now 8.10, chapter 8 talks about linear transformations, where these guys talk about, 4.10 talks about matrix transformations. The difference is the following. 4.10 is like, okay, suppose you can represent a linear transformation using a matrix, then these are all the things that result. Chapter 8 basically says, oh, actually, you will always be able to do that. So now let's go over this in a more general sense, right? So that's where, but we're going to kind of take that for granted, i.e. T is a function from V to W with T of little v plus W equals T of v plus T of W, and T of k times little v is equal to k times T of v. This is called here the addition property. This is called the homogeneity property. This together. So here, V, W are vector spaces. Let's call these V1 and V2. Because I want you to realize that they're both from V. Let's be a little bit suggestive here. V1, V2 are in V, and K is in the field. So if I have a function that goes from between vector spaces from V to W, such that if I apply the function to a sum of vectors, it's just applying the function to each vector individually and it's summing that together, and applying the function to a scalar times the vector, I get a scalar times the function applied to the vector. This is called a linear transformation. This is the definition of a linear transformation. Right? Because that is how, for example, you would describe a plane that passes through the origin that is also a vector subspace of this larger space it's in. It has to have these two properties to fit all those 10 definitions that we have for a vector space. And so then there is some matrix A m by n, so that I can think of t of x, applying this to a vector, is equivalent to taking that matrix and multiplying by that vector. And that's the sense in which we mean. So let's actually look at that a little bit. Where tell me what you would think m and n are, based on what we've said. It's been a while, but
What do you mean by that? What do you mean by that?
I mean, it's the new dimension.
I just told you the dimensions of the matrix. So given a linear transformation, a function that connects two vector spaces over some field, if these two properties hold, I am saying that there will be a matrix of size m by n that can describe this function in terms of matrix multiplication.
Okay, so the number of components of your output, vector AX.
Okay? In terms of language that we've been covering in chapter 4.
Rows and
Sure, m is the number of rows, n is the number of columns, but what is that? What do the number of rows represent? What does the number of columns represent?
The dimensions of your input and output.
Sure, which one? So this would be the dimensions of?
The new and the old.
So m, the number of rows, is the dimensions of your output. So this would be the dimensions of v, w. And n, the number of columns, would be the dimensions of your input. That would be the dimensions of v. Now in 4.10, technically they said, okay, we are pretending that we can express these two guys as f to the m cross and f to the n. But here I'm just saying, we can do it in general. If we know the field that they're over and we know they're finite dimensional, then there will be a matrix with these of this size that can represent that linear transformation. In what sense? I mean, we've actually constructed this a little bit before. So why? Or maybe the question is how? What would you be thinking of?
Why and how what?
Random vector space.
Uh-huh.
I give you a random function with these two properties.
Mhm.
I'm saying there's a matrix that represents that function. How would you go about constructing such a matrix? What would its components be? I know there should be m rows and n columns, at least I'm telling you. Just as an idea, how do you think you'd go about creating such a matrix?
Would it be a transformation matrix? Like a kind of transformation matrix?
Sure, but tell me a little bit about how you would form such a thing. Tell me why this idea makes sense, or why it should make sense. Like I said, okay, I have a linear transformation, I can represent it with a matrix as long as these things are finite dimensional. Why does that make sense to you?
Because matrices represent functions?
That's what I just said though. Why would you think? How do you construct such a function so that you can get matrices involved? Yeah.
Did you find a basis in V and W, and then?
Okay, so let's look at the bases, right? So we've been talking about that over the past week. So this means for all V in V, I can write this in terms of some basis vectors, right? So I can say V is going to be something like, I don't know, C1 V1 plus C2 V2 plus C, what am I saying is the dimensions of n? Cn Vn. Right? And for all little w's and w's, I can represent w to be d1 w1 plus d2 w2 plus dm wm. So how are you thinking of connecting these two?
okay, so it's now more concrete now.
Now, what I'm saying is there's a function that will take something like this as an input, output something like that as an output. Now how would we go about constructing such a thing? Let's just ignore the basis vectors. I'm thinking of an ordered basis, so that's kind of superfluous. So I can somehow kind of link this guy to some vector like C1, C2, all the way to Cn, where it's understood that these are the coefficients of some ordered basis. And similarly, I can link this guy to some vector like d1 through dn. And so basically, it's kind of like my t now is going to be equivalent to something that's going from the input space, which is going to be v. So that would be v fn to the output space fm, right? And I don't remember, it's probably the first lecture, the second lecture, I actually showed you how we go about, we've seen how to obtain a matrix from this. In the R2 and the R3 case, we can do some sort of induction argument to say that. We can expand this for multiple cases, right? So we did matrices, remember, where we called it, I think, PQR, and then we asked, oh, if we add these two, what would we get? If we compose these two, what would we get? And then I said, oh, we can write these as matrices, and then matrix multiplications like composition, and blah, 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 right? So that's how you kind of make this connection, right? If I have a function between vector spaces, I can think of it as a function that connects elements that look like this. But then if I just ignore the bases and focus on the coordinates and focus on their coefficients, I can create coordinates that live in this space. And so this function is equivalent to that function, right? And by forming this function, now just focusing on coordinates, if I start to arrange them in such a way that I can see inputs and outputs without worrying about the variables or the bases that they're attached to, that's how you form matrices. We actually constructed some of these, and you would construct them in exactly the same way. So it means that if you have something like this in general, you would in general be able to find a matrix that this function is described via matrix multiplication, right? And remember, matrix multiplication is actually a composition. So this is like taking X and plugging into the matrix and then getting the result, which is similarly what a function means. You take something and you plug into the rule of the function, and it gives you a result. Right? So that's a very important conceptual jump that we can now make, and we can make that jump because we have things called bases. And that's why things like bases and linear independence and all that was important. It allows us to make this construction. And making up this construction allows us now to think of any linear transformation on any vector spaces, no matter how they look, what they behave like. I can describe them in terms of matrices. Once I know how to describe them in terms of matrices, now I have things like the equivalence theorem that will tell me how these guys all play between each other. And I can know in the equivalence theorem that is very useful when it happens to be that the dimensions of my input and output are the same. Then in that case, I know a bunch of things all at once. Once I can verify any one of these properties, which will usually verify the easiest one, then I'd be able to use that everywhere, right? And I can use A through K, all of those items will actually follow, right? So 4.10 and chapter 8 are sort of based on this idea, the fact that in general, if we can create functions of this type, in general, by looking at coordinates, we can talk about them in terms of matrices and matrix multiplication. And so now we're going to start to look at some consequences of this conceptual jump and how we can describe the functions and the sets they work on. So I don't want to do it again because it's going to take up too much time, but you can go back and watch lectures 1 or 2 or wherever I did that example to see how you go about actually constructing those guys. And you'll notice now you can watch that with a newfound understanding. You can realize that, oh, when he's making the coordinates here, he was using the standard basis. It could have been another basis and the idea would remain the same. Right? So in the examples when we actually did this in R2 and R3, I was doing it in terms of the standard basis. I was constructing matrices. But in terms of some other basis, we can still use matrices. The entries would just be different in different positions. But all the conceptual ideas would remain the same. just some notational ideas. Where either myself or the text might get lazy in typing these things, and so you'll often realize that there are some shorthands that might happen. So sometimes instead of writing t of x, right, to say, oh, this is a function, they just might write t with an x beside it because they're thinking of t as a matrix and they're multiplying it. They might write t in straight brackets, and they might have, or a notation, and they might put t of x in brackets. You should just realize that these are all saying the same thing. And they use this especially. These kind of notation is especially. When we're thinking of the function in terms of its corresponding matrix. So there are some times where they're going to talk about functions and what they're saying applies just because it applies to all functions, right? But then there are times when they want to say something that it only applies to the function if I can describe it by a matrix, and so they'll use this notation as opposed to that notation. I'll study time. So, moreover, for two linear transformations, so I do TA and TB. Let's say this is from Fn to Fn, and this is from Fm to Fn. We can define their compositions. TB composed with TA, which we'd often just call TBA, the amounts. And it's defined in terms of the kind of expression you want. That's just actually the matrix B times A. Where the matrix of TB is B, and the matrix for TA is A. i.e., this is the matrix that represents the function TB of x. So this means I can write TB of x as b times x, and I can write TA of x as a times x, and TBA of x is just going to be the matrix B times A times x. So we're connecting the general to the more specific. And note by above, how far above we wrote it, we can think of V being somehow equivalent to Fm and W being somehow equivalent to Fm for some n if both are finite dimensional. And how do we do that? Set up an ordered basis, take the coordinates. They will live in this space. And each vector can be uniquely represented in terms of those coordinates with a certain specific basis. And so this will be 1 to 1, it'll also be onto. And by the vector space properties, the 1 to 1 is clear from just that. The onto part you get from the vector space properties that says, once you have a vector, then any scalar multiple of that vector must also be in the vector space. So this tells you that not only can every vector be described in a specific set of coordinates, but if you come up with a random set of coordinates, it will describe some vector, because multiplying by any random coordinate gives you a vector in that vector space. And adding two vectors in a vector space will give you the vectors in that vector space. So if you give me a vector, I can describe with a random coordinate. There is some coordinate that describes it. Give me a random coordinate, I can map it back to some element in the vector space. So these two are interchangeable. And so in general, I can think of two vector spaces. Once they're finite dimensional, I can think of them in terms of tuples in a field. And once I can think of them as tuples in a field, I can then construct matrices that would describe that function. Once I can describe that, now linear algebra, we can use that. I don't know if I actually drew the diagrams for you guys. I've been talking so much about functions in different contexts now, I don't remember who I told what. Is it even important to draw this? I don't know. If we can look at some illustrations here. It's probably not as important for us as it would be for the 308 people. But so let's say you have some TA that goes from Fm to Fn. How you can think of that is, here is some vector space Fn, which might be equivalent to some other vector space that you're thinking about. And here's some other vector space Fn. And it will take a vector here, x, and it will output to the vector a times x in that guy. And the dimensions will be determined by m and n. You can just do multiply. So you can actually describe this function in terms of a rule. Multiplied by a times m n, the appropriate one. And so the set of all things over here that are assigned, you can call that the range of t. Right, all the language you're used to with functions will work here. So this guy is your codomain. This guy is your domain. The codomain might not be, not necessarily everyone here will be assigned. For example, you can take a constant function, multiplication by the zero matrix. All of them will go to one guy. So there'll be a bunch of guys that are potentially missing here. But a bunch of guys that are assigned, we call them, they are the range of the transformation. This set here, everyone here gets assigned to someone, that's called the domain of the transformation. And for any random vector space, I can think of them as equivalent to this once they're finite dimensional. And so I can describe this rule that assigns vectors over here to vectors over there by multiplication of an m by n matrix. In the event that I want to do a composition, so let's say TA goes from Fm to Fn, and TB goes from Fn to P. What we're having here is that we have a set Fm, here we have a set Fn, here we have a set Fp, and I can have a vector here that is mapped to a vector over here by TA, and I can have, that will give me a vector here which I can call TAX. Then, if I plug into this function, it will take it somewhere over here, that's your TB. That will give you the output TBA of X. If you look at the composition, that's the guy that goes all the way from here to there, cuts out the middleman, simplifies the function. The function that takes it all the way from the start to the end without worrying about all the details in the middle, that guy is your TBA. Right, so this is the domain of TA, the codomain of TA, where this is the domain of TB, the codomain of TB. What else do we want to say here? And I feel like I did examples of this here, but let's. Examples. Yes?
Is it, so it's TATB, but if you go all the way over, it's TBA. Is that inversion intentional or?
It's not an inversion, it's a composition.
Okay.
Right, it's kind of like when you were talking about functions like back in calculus. I didn't talk about a function that goes from A to B. Right, so here is your x. When you plug it out, you get f of x. Right? If you have a function that you call g, then what you do is if you take that and plug it into g, you get g of f of x.
Oh, I see.
Right? So f would do one thing. You can take that, plug into g, it will do something else. But if you want to know how to get all the way here, well, it was just g of f of x is the rule, right? The composition rule. I'm saying these guys are functions, so the function composition works in a very similar idea. Right? To figure out elements here, just by using here, we don't need to worry about f necessarily. We can create a whole new rule that connects this to that. And that rule would be the composition. These two can be different, by the way, in the sense that so good. And here's where you might see the difference between all of these. Here, let's say in terms of matrices, if you look at TA, the matrix for TA, this is some matrix of what dimension? If you look at TB, this is a matrix of what dimension? And if you look at TBA, this is a matrix of what dimension? So A would be what?
N by M.
Come again?
N by M.
Right? Because the number of columns is your input dimension, the number of rows is your output dimension. This guy would be?
P by N.
P by N. Notice that I can do the matrix multiplication BA, which is what we expect to be able to do, because the inner numbers are the same. And we know the result should be this guy, right? The outer numbers should be the dimensions of that. So this will be P by N. Right? Which, if you look at where the start is, the input dimension would be M, the output dimension would be P. And so you can have very different rules here, right? So it's not like, it's not like you're always going to want to think of this as a product of two things. Sometimes you just want to not have to worry about how many things I have to multiply to get here. Just give me a new rule that gets me here right away, right? And that would be this size matrix, as opposed to worrying about multiplying two things of those sizes. Yep.
This might relate more to through-weight, but does our field have to be numbers, or are we looking at that in different functions in a different context in classes?
Oh, fields don't have to be numbers. They just have to obey the field axioms.
Oh, just
So we did look at, for those of you in 308, Z mod P, this can work, where P is prime. So that is a finite list of things that will have all the properties of the real numbers, and so you can talk about a finite set. You can do this in any case. So your field doesn't have to be the real numbers, it can be anything. Many ways to construct fields. Let's move on. Examples. If I look at f from R to R, f of x is x squared, and f from R to R, f of x equals 2x plus 1 are not linear transformations. Previously shown, this is way back, this is like lecture 2 or 3. Whereas f from R to R, f of x equals 2x, for example, is a linear transformation. We realize that this obeys the two properties that makes a linear transformation. That doesn't. It also means, in fact, that there is a matrix that I can use to represent this. Of course, it's going to be a 1-by-1 matrix, it's not going to be very exciting at all. But now when you start to go between like R to the n, where this is something bigger than 1, then you start to get matrices of various sizes. Maybe you can construct one. Let's say f goes from R2 to R2 by f of x equals, let's be a little bit more specific, f of x equals f of, say it's a 2D coordinate that I'm taking, and then it outputs to another 2D coordinate, say ax plus by, and cx plus dy. And you can sort of think of the x as a placeholder for the first basis element, whereas the y is a placeholder for the second basis element. And so we can even just worry about the coordinates. And so this is equivalent to some sort of matrix multiplication, a, b, c, d, multiplying the xy. So I can describe a function. I will be able to write it as a matrix as long as it's a linear transformation. I won't be able to write it as a matrix otherwise. And this is a linear transformation. To really understand sort of the things that I'm writing down on the board, you kind of had to have been paying attention the whole semester, like from lecture 1, because I'm really putting a lot of those ideas together now, and I realize it's going quickly, but it's because I've already actually laid the groundwork. Under the assumption you've been paying attention the whole time, I shouldn't be saying anything too confusing right now, even though it might seem like I'm all over the place. It's just that I want to give you a lot of facts. There's an infinite number of ways these things can be applied, so I just want to okay, here are some examples of me applying this. Example. Let's say f from C1 to C1 by f of x equals the derivative of x is a linear transformation. And given by f of x equals the antiderivative of x is a linear transformation. These are some other examples. These facts is kind of why we can apply this to differential equations. Because we really only deal with integrals and derivatives of a function.
This is random. Did we do this like way back, like the same, something similar to this, like early on in the class, like these examples? This feels like you brushed past this like the second lecture or third lecture.
Yeah, that's what I'm
Okay, just
It's just that at that point when I did it,
conceptually have any underpinning for, okay.
there was no conceptual underpinning. I was just saying things that you guys have seen before, and like, yeah.
Okay.
Now I want you to look at the same things
And
again.
think about it in context.
But now be thinking about, oh, there's a basis in the background
Okay, I see,
somewhere.
I see.
There are these constants, they're coefficients of some ordered basis, and that's why we can make these jumps.
Okay.
And that's why I can prove all these theorems that sometimes you're wondering, how do these guys come up with this stuff?
I see.
It's because they really just took something familiar and looked at it in a completely different way. And then now it's like, oh yeah, all these nice facts fall out of it. Right? So you look at something like the existence and uniqueness theorem from differential equations, it's linear algebra in the background. They figured that out because, oh, just think of these guys as vectors. And there's a matrix, and we can do this with the matrix, right? So the matrix has to be invertible because we're going from Rn to Rn, and then that means that we can do this and we can do that, and this has to have a unique solution. And so the solution has to have this form, and this has to happen, and that has to happen. So yes, I've either specifically written these on the board before or at least mentioned them, so it should seem familiar. But right now I want you guys to get into the habit of thinking of it in the linear algebra way,
Gotcha.
not in the calculus way necessarily. And I believe I also spoke to you guys about being one-to-one and onto before. So let's actually remind ourselves of that. So let T from Fm to Fn be a linear transformation, and T is called one-to-one if someone who's not in the 308 class. What does it mean to say T is one-to-one?
That every of the values assigned in the codomain is assigned to exactly one in the domain? Is that backwards?
If things in the codomain are assigned to exactly, well, the function assigns in this way, so you can't really say it like that.
There's a unique value for every.
Each input will go to a unique output, right? Which means if I know the two outputs are the same, they have to have come from the same input. That means if T of X is equal to T of Y,
There's exactly one.
then X and Y must be the same. Because every input has to have a unique output. Give me two outputs that are the same, they had to come from the same guy. So that's what one-to-one is. So you can have linear transformations that are not one-to-one, but one-to-one is going to be important for us as well as onto, right? One-to-one, this is AKA injective, or an injection, AKA, very rarely people write out the words one-to-one, but I'll usually just write 1-1. Definition, T from Fm to Fn is called onto or surjective if someone who's not in 308
Every element of the codomain has
for
a-
all y in the codomain
Has an assigned value in the X domain?
there is a value in the domain, there is an x in the domain
such that
that was assigned that guy, such that T of X, the output of that is Y. Right? In other words, i.e., the range of T is its codomain. Let's define that. What do I mean by the range of T?
The set of all values in T.
Then the range of T, which we kind of abbreviate by around T, is, what is it? It is a set.
Of all outputs,
It's a set of all things that live in the codomain such that T of x equals that for some x in the domain. Right? Or you can say i.e. for some x in specifically Fn. So I'm looking at the set of guys that were specifically assigned. So I can look at, so example, I can say T of x equals the 0 vector for T goes from R2 to R2. Then here I have the domain is R2 and the codomain is also R2. However, the 0 vector in R2 is literally the only range element. Every element here is going to go to that element. And so all the other guys out here, they aren't in the range. So in this case, the range is the set with just the 0 vector. In fact, as we've learned today, that is actually equivalent to saying something else in precisely this instant. Do I say that now or later? A little bit later. Let's define another definition. And a part of this is because we're again going to expand the equivalence theorem, so I'm defining some new terms for you. But also these are fundamental spaces to study in their own right because they will tell us about the vector spaces that the functions are connected. So the set T, this is the set of all x in the domain such that T of x is the 0 vector in the codomain is called the kernel of T. Notice this is the same as the null space of A. Right? So the kernel of a linear transformation is precisely the null space of the matrix that represents that linear transformation. All right, so you can already see how the linear algebra is sneaking in here. That's the kernel. If the kernel of T only contains the 0 vector in the domain space, then it is called trivial. So when you talk about something having a trivial kernel, that means the only guy who maps to 0 is the 0 vector itself. So here's the theorem. Let A n by n be a matrix representing TA from Fn. then the following are equivalent. We're going to connect here the inverse of the kernel to the range to the fact that it's 1-to-1. If A inverse exists, 2. Knowing that A inverse exists actually tells you the kernel, let me write in this certain order, the kernel of T is only the 0 vector. The kernel is trivial if the inverse exists. Another thing we know, 3. The range of T is all of Fn. That is to say, TA must be onto. Or T is 1-to-1. So if you're going between two vector spaces of the same dimension, and you can describe it by a square matrix, in the event that that matrix is invertible, what it means is your kernel will only have one element in it, the function will be onto and 1-to-1 at the same time. And by the way, you should realize that it goes the other way as well, which is where we're going to start going to, where if you can connect two vector spaces with a function that's 1-to-1 and onto, it will imply that it can be described by a square matrix that's invertible, which therefore will imply that the vector spaces under consideration actually have the same dimension. The fact that they have the same dimension, you can think of them both as being equivalent to this vector space. And so essentially they'll behave exactly the same way, even though their elements might look different. Right? You can condense them to a situation where they're just equivalent to coordinates, which are the scalars of the basis vectors, and those guys are just elements of Fn, where F represents whatever field you're looking at.
Professor, this is part of the equivalence theorem, right? You're just giving like a functional analog of it?
Yes.
Okay.
So maybe just like talk me through it then. Like how would you talk through the proof of this?
Well, 2 is...
So you have to show that this implies, that implies back to this. So knowing A inverse exists, how do I know that the kernel is trivial?
Because the reduced row echelon form is...
The reduced row echelon form is the identity. Therefore, if I augment that with a 0 vector, I would have each pivot equals 0. And so it will only be this. Or you can go to the fact that AX equals B must have a unique solution. So if we choose B equals 0, we know 0 has to be a solution. We did prove that a matrix times a 0 vector has to be the 0 vector. And so this is invertible, tells us from the equivalence theorem that AX equals B must have a unique solution. So if I set B equals 0, that solution must be 0. And since it's unique, that has to be the only possible way to solve that. Right? Knowing that that's the only possible way to solve that tells you that, what? How do I get to this part?
You know that the vectors in the matrix that represents T would have to span the field A? No.
Wait.
Oh, right. You can say the row vectors have to span, are a basis for the codomain space.
Yes.
And so every element in the codomain space can be mapped to from some element here. You can again use the fact that AX equals B is consistent for every B. So if I take any B that lives here, there is some X that will solve it. this is 1-to-1 comes from the fact that the reducer echelon form of A is the identity. So literally,
It's uniqueness, right?
every guy will have a unique solution. Okay, cool. Did I want to prove this? Um, Let's single out two items here to prove separately. But I want to prove at the level of more like a linear transformation in terms of matrices, or more at the level of vector spaces in terms of matrices. So let T from Fn to Fn be a transformation, linear transformation. Then the kernel of T equals 0 if and only if T is 1-to-1. I planned on proving that a little later, but I think it's nice to actually prove it at this point. But the idea here is, it's useful to actually have an alternative way to think about this because it can show up sometimes, and I'll definitely ask you problems in tests and quizzes where this kind of way of proving things would come in handy. So notice here I'm not really specifying, I'm not really calling it T sub A, so I don't necessarily want you to think there's some matrix in the background. Just purely thinking at the level of vector spaces, how would you actually prove this? So I want an alternative proof here, which doesn't really appeal to the equivalence theorem. You know, but there's probably a subtle way to prove it. Let's go this way. Assume the kernel of this transformation is trivial. We show T is 1-to-1. What does it mean to show T is 1-to-1? Right? You need to show, what do you need to show here?
That there exists an x such that T of x is equal to, no.
That's onto.
Yeah.
You can't mix them up. Being onto is sort of a mixture of a universal and existential quantified statement. But 1-to-1 is not. 1-to-1 is an implication.
So,
T of x equals T.
You have to show that if T of x equals T of y implies that x equals y. That's what you need to show. Okay. So assuming the kernel is trivial, why does this have to be true? Assume T of x equals T of y. How do I get to the point to say that x equals y without really thinking of this as matrices?
well, if you write, what's the vector space here? Okay, so if you write out any vector, no. Does it have to do with,
Oh,
a linear combination of vectors?
There's an easier way.
Okay.
If you go down that road of constructing a linear combination, then you'll ultimately want to be able to say I can construct a matrix and use matrices.
Okay.
But you can actually do it at a higher level.
Do we assume the contrary?
And assume x does not equal y?
Yes.
Okay, so that means you want to say that the kernel, you contradict something. Here's a pro tip, and I'll probably state this officially for the record. But here's a tip. T goes from a vector space to a vector space, right?
Yes.
Which means that here, there's some guy that lives in Fn, call it x, then there is, its output is T of x, right? In F, also in Fn, right? So the tip is the following. You need to realize that both of these guys, x and T of x, they are vectors. They are members of a vector space. Meaning, any of the 10 axioms for the vector space axioms can be applied to T of x, T of y, can also be applied to x and y. So you do know things like negatives exist. You know things like scalars, scalar multiples exist, all that stuff.
T of x minus T of y equals 0.
Yeah. We know that the negative exists, so I can actually subtract T of x from both sides. Right? Because these are members of a vector space. Now, because this is a linear transformation, you see this? We prove that the negative of a vector is the same as -1 times that vector, right? So in other words, I can think of this as -1 times this guy, right? Which means I can actually move it in because it's a linear transformation. But now I have a sum of outputs. I can turn that into what? Well, the output of the sum.
Inputs inside one.
Right, skipping a step here, technically you'd write this is x plus the negative y, but whatever. You get what I'm saying. And so what does that mean? This means x minus y is an element of the kernel. Right? Because what is the kernel? It is the set of inputs that when you plug in, you get the 0 vector. But that would mean that x minus y must be the 0 vector. This is the only guy in the kernel. Let me just...
Oh, it shows that x is equal to, yeah.
Since the kernel has only that one guy in it. If you're in the kernel, you are that guy. But then, now these guys are members of a vector space, so its negative exists, the negative being positive y, and I can add that to both sides. And I get x equals y. Right? Now again, there is the temptation here to think of this in purely algebraic terms like algebra that you know from calculus, but you need to understand that I'm making these steps in the background because there's a vector space axiom in my mind that I'm applying. I'm not just willy-nilly doing this, right? To be able to say this, it's me saying, oh, these guys are elements of a vector space, so negatives exist, and I can add negatives to both sides. If I take something plus its negative, I get the 0 vector, and that is the definition of a 0 vector. I know there's a 0 vector because it's a vector space. So me jumping from this step to this step, there are like 2 vector space axioms that went through my mind that told me that I could do this, right? Like every step, you need to justify. It's one of the things that makes a class like this or any proof class very hard because you're used to just doing things without really thinking about what you're doing, but that ends now. Like math is not that anymore, right? Everything requires a justification. Okay, so it turns out that this is true. If I assume the kernel is trivial, it must be one-to-one. Here's why. We're in a vector space. All this has to happen. let's go the other way. What if I know it's 1 to 1? How do I know that the kernel is trivial?
Oh, one guy, but only one, since it's 1 to 1, only one vector.
Well, we can know that t of 0 equals 0, right? And why can I say that? Maybe that's something we need to justify. I'm not sure if I specifically justified that before. But since t is 1 to 1, this is the only element that maps to 0. Which means the kernel is only that guy. Right? So I know the kernel must include that guy, but since t is 1 to 1, that has to literally be the only guy that will solve that equation. Because if I assume there's some other guy that maps to 0, then t of this will be equal to t of that, and then I would imply that those two things are equal because it's 1 to 1, and then you'll be assuming something's not equal, and you'll get a contradiction. So that ends the proof, by the way. But I don't remember if we actually justified this, so let's make sure we can realize that we didn't just say something silly. Why is that true? I didn't specify the transformation, but I'm saying that is pretty much true for every transformation, which is why I could say that. It's a tautology.
Because of the second, let's say we have t of 0, that's equal to t of 0 times the whatever scalar represents your identity.
Okay, so you're using the homogeneity property?
Yes. Therefore, you can pull out the, you can pull out the, no.
Or do you want to say that you want to use the identity for the field specifically?
No, never mind. I thought 0, the 0 vector was a scalar for a moment. I don't know.
Oh, okay.
So,
Well, I mean, could you do that? Take out the 1, and then the output, the image is a vector, right?
Sure.
And then by the axiom, there was a thing that you proved before that one time.
Yeah, but you just get that this is equal to itself by doing that.
What if we used like different ones instead of 1? Would that the same thing happen? Or like say represent
let's
like,
use the 0 scalar.
using x and negative x or something.
T to 0 plus T to 0.
I like that one better. The scalars, it'll be kind of weird to use, because then if you use a 0 scalar, you have to worry about division and stuff like that. But we do know by definition that 0 will be, take any vector in the vector space and add its negative. So I can add plus minus 1 times x, which is just minus x, so I can have this expression, which we know is what?
They're both vectors. So you could take t of x individually, taking the transfer.
So what I would actually say here specifically, this is nicer, I think. Just do 0 and 0. And then that's true,
And by axiom 4.
which means t of 0 is 0 by axiom 4. Right, we did actually a similar proof to this, right, where we showed that 0 times the vector must be 0. But I didn't want to do that here because then that means I'm thinking of some sort of multiplication here, which I didn't really want to think of it that way. But this is true because 0 is in a vector space. That is true by the addition property of a linear transformation. Then to this guy I added that and I got himself, so that guy must be 0. So saying this was okay. in my Theory 8 class especially, that was a big issue. People were just saying things that they thought made sense, but it didn't. Sometimes because it made sense in some context, but it just didn't make sense in the context they were talking about. So. Let A represent a linear transformation. So it's a matrix, but I'm thinking of it specifically as a linear transformation. Be as in the above theorem. Then there is an inverse transformation. By the way, specifically, this will be represented by the inverse matrix. And you can think of inverse here in the sense of functions, you know, like when you have invertible functions. So there will be, we'll denote this guy by T inverse, denoted T inverse of X, or T inverse. And of course, this is such that this guy is also an invertible linear transformation, such that where T inverse composed with T of X is X, and T of T inverse of X is X, i.e. the composition of these two functions will be the identity function. This is like we're seeing what we did in 08 all over again today, just in a different context.
Sorry, just
Yeah.
T, I'm a little confused now. Just isn't T just some arbitrary transformation from one, I don't know, one function to another?
No, I'm specifying that A is a matrix as in the above theorem. So I'm assuming that T is a transformation that can be described by an n by n matrix. So I'm looking at vector spaces that have the same dimensions.
Okay. Oh, so those are
I'm
the
also
properties.
looking at the case where it's invertible, where the matrix specifically is invertible. And that means once you can find a transformation going to this, from this vector space to that one, there's also a transformation that goes the other way that literally undoes what the first transformation did.
But then, I guess, aren't these all implicitly true because they're just a subspace of, like, matrices? Like, the space of matrices? Like, if it's true for...
Here, I would think of this as a subspace of functions as opposed to probably matrices.
Okay.
I think it will follow easier from that. Thinking of its functional nature allows me to say this a lot easier, I think.
Okay.
There are other things when thinking of it as a matrix is also easier. Can be easier in that context. So we can now add more to the equivalence theorem. So let A n by n be a matrix and now you just slip in another little assumption that perhaps represents a linear transformation. So you can take it or leave it. Then the following are equivalent. We had A all the way through K, same as before. So same as in 4.8. Now let's add some things to that. Hij, Is there anyone who, if I give you a random letter, you immediately know what came before and after that? I always have to start singing a part of the song before I realize what comes after K. Okay, that's L. The kernel of the transformation is going to be this. So I'm pretty much adding the last part of that theorem to this guy. The range of the transformation is all of Fn. And the transformation is 1-to-1.
Could we replace M and N with just saying T is projective? Would that be okay? Is that the same?
Yeah. Yeah, they listed separately because you want to, sometimes you might not need both.
Yeah.
You just care about one or the other. And so the equivalence theorem fleshes out all the minute little facts that you can know. Once you know it's 1-to-1, you'll automatically know it's onto if it's going from, if the two vector spaces have the same dimensions. So usually for bijections, there are two things you have to verify, whereas when they flush it out this way, you only have to verify one of them. That's all for 4.10. On Tuesday, we'll go through chapter 8, which is again, it's covering all the stuff that we did here. They just go a little bit more generally. I will also give you some specific examples where we're applying this to problems that might show up on a test. So we'll do that on Tuesday. On Wednesday, we'll talk about eigenvalues, eigenvectors, and diagonalization. That's going to be actually a very computational kind of thing, so that should be fine. And on Thursday, we have our test. On Thursday, the test will only go up to what we finished on Tuesday, so you'll only be responsible for up to chapter 8. I'll put the eigenvalues, eigenvector things in the bonus section. So if you can learn it quick enough for Thursday, that's great. If not, you don't need to really worry about it. But it will definitely come on the final. So that's where we're going. So now we're kind of wrapping things up. So we started off the course talking about, in general, this sort of narrative that we wanted to build. We got lost for a while looking at matrices and we're like, what does this have to do with anything? And now we're kind of saying, okay, remember all that stuff I told you? Let's connect them all. And you realize that all that stuff I said was made possible from the idea of bases and coordinates and all that stuff. We can get the matrices out of everything. So we'll stop there. I will see you guys next week. I'll post some homework problems to work on, either tonight or early tomorrow morning, and then you can start to get some practice.